we'll start with my slides. I hope everyone can see.
Yeah.
So we're talking about asynchronous domain decomposition methods for the solution of PDEs. I don't expect anyone to know any of these things, but we'll see where we go. So first of all, I want to acknowledge the help of many of my collaborators. Eric Womar from Sandia, Mireille El-Haddad, she is originally from Lebanon. She did her PhD in Paris. She's now in Quebec. She was a postdoc with me. Jose Garay was a student with me. Christian Glusa is at Sandia, and a very dear colleague in Paris, Frédéric Magoulet. So, so I will start by decoding every one of these things. What is domain decomposition? What are optimized Schwarz methods? I'll talk about optimized and talk about asynchronous methods. I'll talk about an application. I'm not sure we have time for 2 letters, but if we do, we can do that. Okay, so the general problem is a linear PDE with some boundary conditions. And all I ask is that the solution exists, that the domain and the equations are smooth. So what are the decomposition? Well, so let me go back to Schwarz. So Schwarz in 1870, he said, okay, I know how to solve a PDE on a circle, meaning, no, he didn't know how to solve. He said, I know that there is existence and uniqueness of solution on a circle and also on a rectangle. Well, what about the union? What about this? It says, well, I don't know if there is a solution for the PDE on this one. You say, okay, let me invent this boundary. Let me invent this boundary and give some crazy values. And now I can solve this. Now there exists a solution on the left. And then once I find the solution, I have values for these artificial boundaries. And then I can solve it on the right. And then he proved that if you iterate this so-called alternative Schwarz, then there is a unique solution on the union. Okay, so let's so as you see, if you have a domain like this one, and as you see, it doesn't even have to be smooth. Then I'm going to invent the boundary for artificial boundaries, and I invent some dish-like condition, and then I solve on the left, and then that gives me values on the blue, and solve on the right, and then I iterate, and in the limit, they have a unique solution on the whole thing. So Schwarz did it in 1970, and about already 40 years ago. So people say, well, Lyon said, I can use this as a iterative method. Okay. Okay, so this is what alternative Schwarz means. It's an iterative method to solve the PDE. Of course, I just described this to you in the continuous, but you can do this in the discretized way. All right. Now, if you have more than 2 subdomains, It's the same idea. So think of it if you have a Zeppelin or a sausage, you cut it in pieces, and you can go from the left to the right, and then back from the right to the left, or you can do them simultaneously, and this will work. Of course, it can also work if you have a checkerboard partition. And so this works. Now, mostly this has been used as a preconditioner for conjugate gradient. So Schwarz, you can think of this in two modes, as a solver or as a preconditioner. And a lot of work on the domain decomposition community consists of proving that for certain problems, elasticity, different problems, this will work, and designing different ways of doing Schwarz. Now, as a solver, this, what I just told you is multiplicative Schwarz. It's also additive Schwarz. And this can be interpreted as either block Jacobi or block Gauss-Seidel with overlap. You see, because we have the overlap. So let me go back to my board so I can try to explain this to you if you're not familiar. So if you have a matrix, right, you can separate it into blocks. And then you want to solve AX equal B, then you can use this block. So solve A11 X1 equal B1 minus A21 X2 and iterate, okay? And you can do this with overlap, in which now you have extra stuff. So this will be, this corresponds to block Jacobi with overlap. And this is essentially the same as additive Schwarz. Now, if you do this like this, this will not converge because you're duplicating the variables. You see these variables here will be the same as these. So there are different ways of fixing this. And as I'll mention later. Okay, so if you think of it this way, when you do block Jacobi or block Gauss-Seidel, the convergence is linear. It depends on the norm or the spectral value of the iteration operator. Now, restricted additive Schwarz is one way of fixing the problem of the overlap counting. So restricted additive Schwarz says, you compute with the overlap, as I show you in that sketch, but then you throw away what you have from the overlap and you only keep the non-overlap variables. In this way, you capture the overlap when your solution, but you don't double count. And this has been shown very useful. This was developed by Szyld and Sarkis as a preconditioner, but it's also very good as a solver. I'll show you some pictures. Domain decomposition is a huge method, a huge field. Here, I just mentioned a few books. There is this website that has the proceedings of the conferences, list of hundreds of papers, domain decomposition method, bdn.org. Then the next meeting will be, they have a meeting more or less every 18 months. The next meeting would be in Prague in July 2022. Okay. Now, what are optimal Schwarz methods? So in the picture that we saw, we invent boundaries. We call them artificial boundaries. And some people say, why, if we invent the boundary, why do we have to have Dirichlet condition? This is not a natural boundary. It's an artificial boundary. So let's have conditions such as Robin or Robin boundary conditions, which is normal plus some parameter times Dirichlet. And then pick the alpha that gives you the smaller spectral radius, for example. And this is called optimal Schwarz. You can get greedy and say, okay, instead of one parameter, let's take two parameters. Normal plus Dirichlet plus tangential. And this is called sometimes 0, 0, 2, 4, because essentially the optimal condition, not the optimized, is a Dirichlet to normal map for those who know PDEs. And this will be the zero order or the second order approximation to the Dirichlet to normal map. Okay. Now, if you want to find this alpha, what's the optimal, then there's a lot of literature for rectangular domains or half spheres in which you do Fourier analysis, and then you find the best alpha or the best alpha data. More recently, there is a kind of an automatic way to do this, so you have to think about it. And more recently, my student, Jose Garay, for special cases, he found a formula to get this parameter. Now, all this is based on the PDEs, the Fourier analysis, etc. But you can also think of this algebraically. Without think, you just take your discretization, you get some matrices, and varying this alpha corresponds to changing the overlap, some entries in the overlap to make it converge faster. This is a graph of a now almost 10 years ago paper. So this is essentially block Jacobi or block Gauss-Seidel, sorry, block Gauss-Seidel. This first line, this top line is block Gauss-Seidel without overlap. If you have the overlap, then the convergence improves. Okay, so if you fall asleep now or have to leave, at least you will remember that if you do overlap, you do better. But then you can improve by doing 0, 0, 2. And there's something called the optimal, which is the Dirichlet to normal map, the discretization version. And as you see, we converge in 2 steps. Just to show that optimize gives you a lot, gives you some gains. Okay. So if you have the optimal, it will convert into steps if it's 2 domains, or p steps if it's p domains. So essentially, it's almost like a direct method. It is a direct method by understanding the appropriate Dirichlet to normal map. It's like a double shoe complement. And with approximations, we have a very fast method. So this is optimal Schwarz method. Optimal Schwarz methods are not new. there are a lot of references, in particular in this relatively recent book, Victor Italian, Pierre Olivet, and Frédéric Nataf. They have a chapter in this book on optimized methods. This is a Cyan book, but there is also a free copy as a report from the France repository. Okay, now, new machines are coming, hundreds of thousands of processors, and the communication is usually the bottleneck. So if you want to do Krylov method, you will have to orthogonalize. So you have to do inner products. So imagine if you have 100,000 processors and you have to communicate to do an inner product, this is going to slow down your computation. So usually, as we mentioned earlier, people run Krylov methods, and as a precondition, they use either RAS or optimized restricted iterative Schwarz. And one of our proposals is reverse the order. Do optimal Schwarz or restricted iterative Schwarz as the solver, and then the local problems of, say, 5,000 variables, then use a Krylov method, or just solve it directly if it's only 5,000 variables. So this is a continuous way of thinking of this solver. So we have this Zeppelin, say, this is just one portion. This is the S subdomain omega, which has overlap, and then everything to the left and everything to the right. So first of all, I'm going to think of zero boundary condition on the outside, mostly because I want to show convergence. So I want to show that the error goes to zero, which is the solution. So my iteration says, okay, for each subdomain, and at the iteration n plus 1, solve my local problem. I call this a local problem with zero boundary condition here, and with some type of Robin boundary condition here and here. So this is normal plus alpha u, for example. Here, you take the information from the right subdomain at the n step. So I have the information at the n step on left and right. These are my boundary values to solve the local problem. Is this clear? Okay. So in this continuous formulation, Nataf and Stuller have a technical report from 20 years ago showing that in this setup, things will converge in P or P minus 1, depends how you count iterations. Essentially, it's enough to get the information across the whole subdomain. Now, we can rethink this problem as a map from boundary values to boundary values. I say, okay, I take my boundary values from the left and right, I solve my local problem, and then I produce boundary values for my left and right for the next iteration. So the variables Z are really the boundary condition. So the map says here, the map says take boundary values solve my local problem, produce new boundary values. Everything else is kind of irrelevant. So this is my iteration now. And optimal Schwarz can be seen as finding the fixed point of this iteration. I have now a product map with the maps for each subdomain. And I want to find the boundary conditions that give me the unique solution to the problem. So while I iterate, I get closer and closer to the solution. My local problem is not the solution of the global problem, but as I iterate, it gets closer to the solution of the global problem. All I need is that the boundaries match. Once the boundaries match, I'm done. Okay. All right. Now, when I do this, the way I think about it is I'm a processor. I'm a processor S, and I own the subdomain S. Okay. So I start and I take the boundary conditions. Now I solve, I finish, I produce new boundary conditions, and then I wait, and then everyone else finishes. And then we'll all start again. This is called a synchronization point. Everyone synchronizes at the end of the iteration. And my second proposal is, let's do this asynchronously. What does it mean? It means don't wait. Just keep going. I start with my boundary conditions. I solve for these conditions. I put it back. I send it to the other processors. Or if it's shared memory, I put it in the shared memory. And then when I finish, I don't wait. I just go back and solve. And if this boundary changed and this didn't, I don't care. I still keep doing it. If none of them change, well, I do the same work. If both of them change, of course, in 3D or in different kind of boundaries, I have information from, say, 9 processors, not just 2. So this is what asynchronous means. I mean, if you think about it, it's a totally crazy idea. This is what a teenager will do. He'll say, well, I don't follow orders, I don't follow rules, I just do what I like. It turns out that asynchronous parallel method for fixed point problems have been around for 40 years at least. There is a long list of references. I just picked a few selected papers and a couple of books. There's a survey that I did with Andreas Frommer about 20 years ago of what has been done until the year 2000, which summarizes everything about this. One result says, okay, I want to solve a fixed point problem, right? This is my product map. If I have some norm for which this is a contracting map, then this will converge. In other words, the theorems that we have say, if the synchronous method works, as long as the asynchronous iterations don't go crazy, things will work out. The theorems don't tell you how fast, just tell you that they will work, that it will converge to the unique fixed point, of your iteration. So we knew that for general problems, in my work recently, we extended this to asynchronous optimal Schwarz method. If you have one-way domain splitting, which is like I just told you, like a sausage, or stripes, then Schwarz methods converge. We proved several theorems. We showed it for the optimal case. We showed it for the operator for the Laplacian on the plane with approximate boundary conditions, not optimal. And also in more recently on a bounded domain, on a rectangle. We also have it with cross points, not just stripes. We are able to do this in a total algebraic fashion as well, again, for this one-way splitting. I will not go over all the details or almost no detail, but just to give you a flavor. For the Laplacian on the whole plane shifted with a positive constant, we divide the space into vertical stripes. So we have the left, the middle ones, and the rightmost. And there is no loss by assuming that the middle ones have all the same width. So consider the restriction of F to the subdomain. And then the synchronous algorithm says, solve my problem using my Robin type condition on the right. For the middle ones, you have the local problem on the domain. And we have left and right boundary conditions, and on the rightmost, we have left boundary conditions. Okay, so this is my synchronous method. Again, we reinterpret this synchronous algorithm as a fixed point map from boundary to boundaries. And for the asynchronous, we just keep going without thinking of iterations. The concept of iterations loses its meaning because I'm a processor, I update, maybe I do it 3 times, the other processor 5 times. So every time I finish, I update. And the theorem says that, and the standard condition of the asynchronous model, the standard condition are the following restrictions. The conditions I read are have been computed before I started, so you cannot read future information. No processor stops working, things like that. These are the standard conditions. And we have some conditions on the size of the overlap and the width of the subdomain that guarantee that this asynchronous method will converge to the solution for any initial approximation. Now the proof is long and complicated. It uses Fourier transforms, and then we get the operator in Fourier space. And then we showed that the max norm of this operator is contracting, and therefore we can resort to that theorem I show you from El Tarazi that shows the asynchronous method will converge. On the rectangle, we can show something different. When we have cross points, we have to use a whole different technique, something called general Fourier series that maps infinite coefficients from one step to another. We have to show that these map certain spaces or sets in the product space that are shrinking. Anyway, we're able to prove all this. So we have the proofs. So I'm going to next show you some experiments. Just to show you some ideas how it works. Okay, so the experiments that I want to show you first corresponds to the Chicxulub crater. So this is in Mexico, in the Yucatan Peninsula in the Caribbean. Chicxulub is a Mayan term. I don't know if you know, I'm Argentinian, I speak Spanish, but Chicxulub is not Spanish, it's Mayan. So an asteroid landed here about 66 million years ago, and presumably it was instrumental in the extinction of dinosaurs. So there is evidence that this happened, in particular in these places. There are things called cenotes. Cenotes is a Spanish word. They are sinkholes. Here's a picture, and all these white things are these sinkholes. And if you never saw one, let me show you some pictures of what they look like today. So this is a picture I took from Instagram. So they are big holes, they are full of water, people go and swim. And these are part of the consequence of this asteroid. So this is not that something fell there and made a hole. The asteroid came, and then there was a like kind of mixing up of things on the boundary. And the Mayans had them as sacred. Okay, so this is what you see today. And here is a kind of reconstruction of a Mayan event. So this is what they look like. Okay. So what we did is we got some data. We took a large finite element mesh, like a box corresponding to 250 by 250 kilometers, by 15 kilometers deep. And we wanted to find the gravitational potential, which is essentially a plus with the appropriate data that we got. And the final element mesh was complicated, but we got a solution. So let me show you some experiments, 3 different discretizations, 2.5 million variables, about 20 million variables, and about 100, say 50 million variables, 250, 512, 1,000 subdomains. This is a machine in France with 1,000 processors, 17,000 cores, and they are not the same. They are of different type of computational cycles. And this is what makes asynchronous methods work, because different processors may take different times, or in your domain, different parts of the domain you discretize differently, more detail, less detail, bigger subdomains. So we run the same code with synchronous and asynchronous optimal Schwarz method with the same constant alpha or alpha and beta. And in order to make it simple, each subdomain will solve the system directly. So here is the picture. So this is one parameter. The numbers of iteration grow about the same way that grows. So this double and then the double again. The time goes way much more. But if you go on, so this is synchronous. But if you go asynchronous, the times don't grow as fast. In fact, this is an order of magnitude faster than this. So 800 seconds. So you put the machine, you go have a little coffee, come back, you have it. This is with the two parameters. So you see, in 5 minutes, you have the solution. Now, as I told you, the concept of iteration loses its meaning. So different processors have different numbers of updates. You see some update fewer times, and some, this is the minimum and the maximum. We also have average, medium. If you take the best possible synchronous, we have about 60% gain. And as you see, nothing changed. All we did is say, okay, don't wait. Okay. Now, the main point perhaps is not that it's 60% faster or even 4 times faster if it's 0. In my view, the first work, or even that it works at all. It's a crazy idea. Why would it work? But it works. But also the potential that you have when we have these million processors. People have done work by joining together computers in different places and running this. By the way, this is a cross-section of your solution, just to show that it makes sense. So far, what have we learned? That these methods, asynchronous, parallel, optimal Schwarz methods, they work. We have theory. Well, we only have theory for certain cases, but we have experiments for different situations, and they work. They are effective on large problems. You can gain, say, 60%. And the more inhomogeneous your network is, the more advantageous it is to think of these methods. Okay. I have more to show you for 2-level methods. I don't know if you want that or if we can have a larger discussion.
Yeah, I think we can go on to the two level. Maybe it will be fine.
Okay. So suppose, even though we had good results, people say, okay, we want to have some kind of scalability. So I'm going to show you experiment with Rust, not optimized Rust, just Rust, which is simpler. And in this example, all the subdomains are about the same size, all the machines are about the same. And we have 3 graphs: the timing, the residual norm, and a kind of convergence factor. I don't think it's necessary to give you details, but it's a conversion factor. And what we change here is the number of subdomains. So the more subdomains it gets faster, and in this example, the asynchronous is slower and it's a little faster at the end. This is something that is interesting. In the synchronous method, you stop when you reach your residual norm, relative residual norm. But in asynchronous methods, the stopping criteria I said nothing about the stopping criteria so far. So if everything is asynchronous, you don't want to stop and say, okay, we will converge and then start again. You want to do the stopping criteria synchronously. So the way it works is you, for example, did my local problem converge? Yes, okay. So I tell everyone else, but in the meantime, things may change because that doesn't mean everyone converge. So as it happened, by the time everyone says, okay, let's stop, we did more work than necessary. The residual norm is 10 to the minus 10, it's 10 to the minus 8. So of course the timing is the same, but we got a better solution. Okay. Now, for the same example, if you take one subdomain 50% less than the rest, this is to simulate a slower processor or a situation in which you need your subdomain to keep it together. Then the asynchronous method is faster and the corresponding convergence factor is better. Okay, this is a two-dimensional example. Now, this is a weak scaling experiment. So each subdomain is maintained at the same number of unknowns. And you grow the problem as you grow the number of subdomains. And here you see that the asynchronous methods grow, the blue is the synchronous, and then it becomes super slow, much slower. And this is reflected also in the convergence factor. Now there is and here, even with the load balance, now there's an issue here, which is that when you grow, the core space becomes larger than the subdomain, and this is part of this problem. But the asynchronous method is unphased because the core space is just like any other subdomain in a way. Okay. Now, when you make one 50% larger, it's not just at the end, but even earlier on, the asynchronous scales, the timing is the same. So that's very good. Here's a three-dimensional example. And here we see a similar situation that when you go to 4 times the subdomains, the synchronous method takes much longer. The asynchronous, it's almost flat. And here, the situation I mentioned earlier of the course space is still smaller than subdomain, so that's not an issue. It's an issue of communication. This is really showing that the communication hinders the convergence of the synchronous method. Okay, so more conclusions. We show three-dimensional calculations with over 160 million unknowns. 6 similar results as the two-dimensional problem. Against gains of factor of 4. Again, the potential. Now, many people, as Professor Moore mentioned, know me from my work on iterative methods. So what are the clear-up methods? Well, we use them inside for large problems. And the other question that I'm asked many times, in the 80s and 90s, people start to abandon the asynchronous methods, mostly because it was mostly for block Jacobi, which is slow. The difference now is that we are using optimal Schwarz method, which is fast. Also, in a way, we were ahead of our times because now is where we have these gigantic machines where communication is at premium. Now, yes. Yes, right here, question. As I said, we can only prove that things converge. We cannot show, okay, this is the rate of convergence. But we take the synchronous method for which we have rate of convergence, say order h squared or whatever. And then we show that this is faster. So it's at least as fast as that convergence rate. I should mention that there is one paper from 2015 by Chaim Avron and at the Journal of ACM that for positive definite matrices, they show some convergence factor. There's a lot of work to be done. I have a paper coming out on linear problems. Most of this work is with several collaborators. Faisal Shawki is my current postdoc. He's from Morocco. There are many papers on my website. This is my website. You can find the paper on Numerical Mathematics, which is the one with the in the plane, the convergence of the plane and the results of the Szyld crater. There are mentioned two proceeding papers from 4 years ago or so, complementing this. The work on the rectangle with cross point took a long time. We just finished a new revision. Now the paper has 50 pages. Lots of work. Recently published a paper on the one-way partition. The paper on the cross grid correction that I just showed you also came out last year. There's more stuff that I did not mention in the talk, but you can find it on my website. Thank you very much.
All right. Thank you very much, Prof. Interesting. So if you have any question, you can ask. But I'll ask the first one. So you know, we talk about the synchronous, the convergence rate for the synchronous. From the talk, I think it's if the problem converges, if it converges for the synchronous, then it means that it converges for the asynchronous as well. And what about if it converges for the asynchronous? Does it converge? Does it mean it also converges from the synchronous?
There is no such theorem, except, but the answer is yes, because the synchronous is a special case of the asynchronous.
Okay.
Because we can say, okay, everyone finishes at the same time, so it's like synchronizing.
Okay. And then, so you are in the asynchronous case, you are considering the problem kind of a fixed point problem.
Yes.
So you don't really think about the operator, if the operator, the behavior of the operator, how the operator looks like. So because I'm thinking of if your metrics, for instance, do you have to consider if it is symmetric, positive, definite, or indefinite, or non-symmetric? You don't consider all these things.
Okay, so the original proofs that we have for asynchronous methods for linear systems, not for PDEs, okay. There are results for M matrices, which essentially are diagonal dominant.
Okay.
H matrices, diagonal dominant matrices. There is also results, I think, for symmetric positive definite.
Okay.
This is for matrices. So if you're thinking of one linear system that way, these are the theorems we have. In the theorems we proved recently, it was mostly for this big operator that corresponds to the Fourier transforms of the Laplacian. So, okay, so that's that. I see a question on the chat. How might your results on convergence of the fixed point method change when the boundary conditions are not linear in them? No. Okay, the theorems don't apply only because, let me think about this. Okay, so the theorems are the way we use the theorems is, okay, we have the solution. Okay, the solution of the problem solves the problem, and then I take my iterative, then I take my iteration, and then I take the difference, and then I look at the error. So I need my operator to be linear. Now the boundary conditions are non-linear, then I cannot use that proof. So the answer is, I don't have a proof. One would have to rethink or have to do it in that situation. Okay, but I have to. Now, there's a paper I'm about to put on my website like next week.
Okay.
In which I'm working with Faisal Shawki, and we solve nonlinear problems, including problems with the boundary, with a two-level method, with a coarse grid. And we show local convergence of the nonlinear problems, including that. So like Newton method, we show local convergence. So you have to be close, and we show them for specific cases. And in some cases, the hypotheses are satisfied. In others, the hypotheses are not satisfied, but the experiment shows it works. So maybe in a couple of weeks, you can look at my website or send me an email, and I'll make sure to send you the paper. I'm going to put my email on the chat.
Okay, great. Thank you very much. I was just going to ask you to share your website, but thank you.
This is my email. My website is very easy. If you know my name, it's easy. My name is Szyld. Daniel Szyld. Daniel because it's in Spanish.
Great, great. Well, thank you very much. I will definitely check out your website.
Okay, and send me an email anytime for this issue or for any other thing.
Fantastic, thank you.
Doug, I have a question.
Yes, please.
I think on slide 9, you did talk about the spectral radius, like the convergence depending on the spectral radius.
Yes.
And I heard you said the convergence is quite linear.
Yes.
But I believe like linear convergence is quite slow. How does that affect your convergence rate?
Okay. So let me go back to the slide to show you the linear convergence. So I'm going to go back to the slide that I had. that comes from this paper from 2012. So here you clearly see that the convergence is linear, right? The point is that it's, if you do the right thing, it's linear, but it's fast. So this is the standard linear convergence, which is slow, but we can get it fast.
No, okay.
Okay. Did I answer your question?
Yes.
Okay. So that's for optimized Schwarz. Optimized Schwarz
Hello, can
has
you hear me?
linear convergence, but it's a fast convergence.
I can hear you.
Okay, so thank you very much for the talk. I am no expert in this area. I just want to ask some few layman questions.
Please.
So in the very beginning, when you show us the circle and then the rectangle going inside, you said that if you want to solve a problem on this boundary, then you have to introduce artificial boundaries. And I would like to know, how do you decide on which boundary condition to use in that case?
Okay, so Schwarz originally was interested in the existence of and uniqueness of solution. And what he was interested in, he was saying, okay, where do I know how to work, for which shapes, or for which domains do I know that the solution exists? And he knew that that exists for the circle and for the rectangle. So if you have, so he said, well, okay, I take the union doesn't have the boundaries. I put there the boundaries to make it a circle or a rectangle. Nowadays, what people do, it's different. It's they usually work with finite elements, right? So you have your domain in 2 or 3 dimensions. And you have a discrete, and you have a triangulation. Okay, etc. And then they say, okay, well, this perhaps is not good enough, but they say, okay, I'm going to separate, and this on the left is omega-1, on the right is omega-2. This is without overlap. And then I grow by one line of triangles on the left and one line of triangles on the right. So now this is omega-2 with overlap. And the green is omega-1 with overlap. So this is how they decide what artificial boundary goes, which is where you have the triangulation. So, so one line of overlap usually is of order H, which is the size of your triangles. So this is how you have your triangulation. So you have your big airplane, okay? And you want to make sure that here is your boundary condition. Here is your separate this domain and the others. Okay, you do a little more. Or here, you have a little more on this side, a little more on this side for your triangulation. Okay, did I answer your question?
Yes, yes. And also another one.
Yes.
So when, I'm just being curious here, when you introduce these artificial boundaries, are you not kind of introducing an error to the problem? And if that is the case, how do you ensure that this error that you are introducing is a minimum one so that it doesn't affect the solution at the end?
So there is no introduction of error.
Okay.
Okay, but here is again the issue that I showed earlier. If you want to do RAS, restricted iterative Schwarz, you solve on omega 1h, you get a solution on the overlap.
Mhm.
Then you throw away the information here and only keep the information from omega
okay.
1. Omega 1 is the same as omega 1, 0, right?
Mhm.
Okay. Then you solve on the one with the overlap, and that gives you good information to get a better approximation to the solution. And then you only keep the information from omega 2, and then you keep going, and this works. There is no new error for the overlap. On the contrary, you have less error because you're having more information.
Okay.
This goes back, I don't know if you're familiar, long time ago, there is, for linear system, there is a work by Varga. So if you want to solve a linear system, AX equals B. Okay, so you have a splitting. And then you have an iterative method. Okay, you solve this, you keep going. And this is what I was telling you, these conversions, the convergence rate corresponds to the spectral radius of the iteration matrix. Okay, and there is something called comparison theorems. That says that the more information, the bigger the M is, the faster it will converge.
Mhm. Okay.
So the philosophy is the same. The more information you have, the faster it will converge.
All right.
If you have A here, you will converge in one step. Of course, should be cheaper. You have less of A, but the more you keep on A, the faster it should go. Okay. So there's a book by Richard Varga, Matrix Iterative Analysis, I think 1960 or 62. There's a second edition in 1980.
All right. Thank you.
My pleasure.
So Prof, what happens if so if I have a parabolic problem? So the example you showed for the Szyld, the example.
Yeah, it's an elliptic problem.
It's an elliptic problem. So if I introduce the time dependent part, and then somehow I introduce a test function that will still make the problem become elliptic again, then we can apply the same ideas in the sense of the asynchronous.
Yes, yes.
Okay.
There's also something else you could do, which I haven't done, but it would be nice if someone does it.
Oh, okay.
Which is, there are these parareal methods.
Yes, yes, yes.
And then you can write the whole thing and then apply the synchronous method to the parareal. So that's possible too. But yes, either way would be interesting to see how it works.
Okay. All right, thank you very much. So any other question, any other question from anyone? Okay, so if there's no question, then thank you all for joining us. So maybe somewhere in August, we will have the Ghana Numerical Analysis Day.